The National Electrical Code, or NEC, Section 310.15a requires the use of Table B310.7 for conductors in a concrete-encased duct bank with more than 3 current carrying conductors in a single raceway. Table 310.16 provides ampacities for conductors installed in air, which does not accurately represent the heat transfer conditions of concrete-encased duct banks. Annex B provides informative material that can be used in conjunction with the code. Annex B specifically addresses the special heat transfer conditions of concrete-encased duct banks and provides the appropriate ampacity table, B310.7. NEC Section 90.3 states that annexes are not mandatory. However, it does not prohibit their use if they are applicable to the specific installation. Given the clarity of NEC Section 310.15a and the applicability of Annex B to the specific installation involving a concrete-encased duct bank, the following steps are recommended. Firstly, explain the NEC requirements to the contractor. Cite NEC Section 310.15a and explain that it requires the use of Table B310.7 for conductors in concrete-encased duct banks with more than 3 current carrying conductors in a single raceway. Secondly, show the contractor the difference in ampacities. Calculate the ampacities using both Table 310.16 and Table B310.7 and demonstrate the significant difference in values. Explain that using the incorrect table could lead to overheating and potential safety hazards. Thirdly, consult with the local inspector. If the contractor remains unconvinced, contact the local electrical inspector and have them review the situation. The inspector can provide an official ruling on a matter and ensure that the installation complies with the NEC. Fourthly, document your decision. Keep a record of the conversations and calculations you made to justify your decision to use Table B310.7. This documentation will be valuable in case of any future disputes or inquiries. When determining the ampacity of conductors in a duct bank, several factors must be considered to ensure safe and code-compliant installations. The National Electrical Code provides guidelines and tables to assist in this process, but understanding the nuances of these regulations is crucial for accurate ampacity calculations. One key consideration is the installation environment. Conductors installed in free air have different heat dissipation characteristics compared to those encased in concrete duct banks. Concrete's thermal properties affect the rate at which heat can dissipate from the conductors, impacting their allowable ampacity. The NEC recognizes these differences and provides specific tables for different installation methods. Table 310.16 in the NEC is commonly used for conductors installed in air or raceways above ground. However, this table is not appropriate for conductors in concrete-encased duct banks due to the different heat transfer conditions. For concrete-encased duct banks, Annex B of the NEC provides more relevant information, specifically Table B310.7. This table takes into account the thermal resistance of the concrete and the proximity of the conductors to each other, allowing for more accurate ampacity calculations. NEC Section 310.15a emphasizes the importance of considering the complete conditions of installation when determining ampacity. This section directs users to use the appropriate tables based on the specific installation method. In the case of concrete-encased duct banks with more than 3 current carrying conductors in a single raceway, Table B310.7 is typically required. While annexes in the NEC are not mandatory, they provide valuable information that can supplement the mandatory requirements. Annex B, in particular, offers detailed guidance on calculating ampacities for underground installations, including concrete-encased duct banks. Ignoring this information can lead to inaccurate ampacity calculations and potentially unsafe installations. When disagreements arise regarding the appropriate ampacity calculations, it's essential to have a clear understanding of the NEC requirements and the factors influencing conductor ampacity. Explaining the reasoning behind using Table B310.7 to the contractor, highlighting the differences in heat transfer conditions between air and concrete, can help bridge the gap in understanding. Demonstrating the difference in ampacities between Table 310.16 and Table B310.7 can further illustrate the importance of using the correct table. Calculating the ampacities using both tables and showing the significant difference in values can highlight the potential for overheating and safety hazards if the incorrect table is used. Consulting with the local electrical inspector can provide an objective opinion and ensure compliance with the NEC. The inspector can review the installation and provide an official ruling on the matter, helping to resolve any disputes. Documenting all decisions and calculations is crucial for future reference. Keeping a record of the conversations, calculations, and reasoning behind using Table B310.7 can be valuable in case of any future inquiries or disputes. In summary, determining the ampacity of conductors in a duct bank requires careful consideration of the installation environment, the appropriate NEC tables, and the specific conditions of the installation. While annexes are not mandatory, they provide valuable information that can supplement the mandatory requirements. Consulting with the local electrical inspector and documenting all decisions can help ensure safe and code-compliant installations. Understanding the principles of heat transfer and their impact on conductor ampacity is essential for accurate and safe electrical installations. The NEC provides the framework for these calculations, but it's up to the engineers and contractors to apply these principles correctly. When conductors are installed in a concrete-encased duct bank, the heat generated by the conductors cannot dissipate as easily as it would in free air. The concrete acts as an insulator, trapping the heat and increasing the conductor temperature. If the conductor temperature exceeds its rated value, the insulation can degrade, leading to potential short circuits, ground faults, and fires. Therefore, it's crucial to use the appropriate ampacity tables that account for the thermal properties of concrete. Table B310.7 in Annex B of the NEC is specifically designed for concrete-encased duct banks. This table takes into account the thermal resistance of the concrete, the spacing between conductors, and the depth of burial. Using this table ensures that the conductor ampacity is directed appropriately to prevent overheating. When calculating the ampacity of conductors in a duct bank, it's also essential to consider the number of current-carrying conductors in each raceway. The NEC requires that the ampacity of conductors be derated when more than 3 current-carrying conductors are installed in a single raceway. This derating factor accounts for the additional heat generated by multiple conductors in close proximity. The derating factors are specified in NEC Table 310.15 cone. In addition to the NEC requirements, it's also important to follow industry best practices when installing conductors in a duct bank. These practices include ensuring proper spacing between conductors, using appropriate conductor insulation, and providing adequate ventilation. Proper spacing between conductors allows for better heat dissipation and reduces the risk of overheating. Using conductor insulation that is rated for the expected operating temperature ensures that the insulation will not degrade over time. Providing adequate ventilation helps to remove heat from the duct bank and maintain a lower operating temperature. In conclusion, determining the ampacity of conductors in a duct bank requires a thorough understanding of the NEC requirements, the thermal properties of concrete, and industry best practices. Using the appropriate ampacity tables, derating factors, and installation techniques ensures that the conductors operate within their rated temperature limits and that the electrical system is safe and reliable. Ignoring these considerations can lead to overheating, insulation degradation, and potential safety hazards. Therefore, it's essential to follow the NEC guidelines and consult with qualified electrical professionals to ensure the duct bank installations are designed and installed correctly. The correct application of ampacity derating factors is critical for safe and reliable electrical system design. The NEC provides specific guidelines for derating conductor ampacity based on factors such as the number of current-carrying conductors in a raceway, the ambient temperature, and the presence of other heat sources. Failing to properly apply these derating factors can result in conductors overheating, leading to insulation failure, reduced conductor lifespan, and potentially hazardous conditions. One of the most common reasons for ampacity derating is the presence of multiple current-carrying conductors in a single raceway or cable. When multiple conductors are bundled together, the heat generated by each conductor can raise the overall temperature of the conductors, reducing their ability to dissipate heat effectively. To address this issue, the NEC provides directing factors in Table 310.15 current that must be applied when the number of current carrying conductors exceeds 3. These directing factors vary depending on the number of conductors and the type of insulation used. For example, if there are 4 to 6 current carrying conductors in a raceway, the ampacity of each conductor must be derated to 80% of its original value. If there are 7 to 9 conductors, the ampacity must be derated to 70%. These derating factors help to ensure that the conductors do not exceed their maximum operating temperature even when bundled together. Another important factor to consider when determining ampacity is the ambient temperature. The ampacity of a conductor is typically based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher than this value, the conductor's ampacity must be derated to account for the increased heat. The NEC provides tables that specify the derating factors for different ambient temperatures. For example, if the ambient temperature is 40 degrees Celsius, the ampacity of a conductor with a 90 degrees Celsius insulation rating must be derated to 91% of its original value. If the ambient temperature is 50 degrees Celsius, the ampacity must be derated to 82%. These derating factors help to ensure that the conductors do not overheat in high-temperature environments. In addition to the number of conductors and the ambient temperature, there are other factors that can affect conductor ampacity. These factors include the type of insulation used, the presence of other heat sources, and the insulation method. Different types of insulation have different temperature ratings, which affect the amount of heat that the conductor can withstand. If there are other heat sources nearby, such as transformers or lighting fixtures, the conductor's ampacity must be derated to account for the additional heat. The installation method can also affect conductor ampacity, as different installation methods provide different levels of heat dissipation. For example, conductors installed in free air have a higher ampacity than conductors installed in conduit. To ensure that conductor ampacity is properly derated, it is important to carefully consider all of these factors and consult the appropriate tables in the NEC. It is also important to use qualified electrical professionals who have the knowledge and experience to properly design and install electrical systems. By following these guidelines, it is possible to create safe and reliable electrical systems that meet the requirements of the NEC. The ampacity of a conductor, which is the maximum amount of current it can carry continuously without exceeding its temperature rating, is a critical parameter in electrical system design. The National Electrical Code, or NEC, provides detailed guidelines for determining conductor ampacity, taking into account various factors such as conductor size, insulation type, ambient temperature, and installation conditions. However, these guidelines can be complex, and it is essential to understand the underlying principles to ensure safe and reliable electrical installations. One of the fundamental concepts in determining conductor ampacity is the relationship between current, resistance, and heat. When current flows through a conductor, it encounters resistance, which causes the conductor to heat up. The amount of heat generated is proportional to the square of the current and the resistance of the conductor. If the heat generated exceeds the conductor's ability to dissipate it, the conductor's temperature will rise, potentially damaging the insulation and leading to premature failure. The NEC specifies maximum operating temperatures for different types of conductor insulation. These temperature ratings are based on the insulation material's ability to withstand heat without degrading. The ampacity of a conductor is determined by the amount of current it can carry without exceeding its insulation's temperature rating. To determine the ampacity of a conductor, the NEC provides tables that list the ampacities for different conductor sizes and insulation types. These tables are based on specific conditions, such as an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit, and a limited number of current-carrying conductors in a raceway or cable. However, in many real-world installations, these conditions are not met, and it is necessary to apply correction factors to the ampacity values listed in the tables. One of the most common correction factors is for ambient temperature. If the ambient temperature is higher than 30 degrees Celsius, the conductor's ampacity must be reduced to account for the increased heat. The NEC provides tables that specify the correction factors for different ambient temperatures. Another common correction factor is for the number of current carrying conductors in a raceway or cable. When multiple conductors are bundled together, the heat generated by each conductor can raise the overall temperature of the conductors, reducing their ability to dissipate heat effectively. To address this issue, the NEC provides directing factors that must be applied when the number of current carrying conductors exceeds 3. In addition to these correction factors, there are other factors that can affect conductor ampacity, such as the type of enclosure used, the presence of thermal insulation, and the proximity to other heat sources. It is essential to consider all of these factors when determining conductor ampacity to ensure that the conductors are properly sized and protected. The NEC also provides guidelines for conductor protection, which includes the use of overcurrent protection devices, such as circuit breakers and fuses. These devices are designed to protect conductors from overloads and short circuits, which can cause excessive heating and damage to the insulation. The overcurrent protection device must be sized appropriately to protect the conductor without causing nuisance tripping. In summary, determining conductor ampacity is a complex process that requires a thorough understanding of the NEC guidelines and the underlying principles of heat transfer. It is essential to consider all of the relevant factors, such as conductor size, insulation type, ambient temperature, number of current carrying conductors, and installation conditions to ensure that the conductors are properly sized and protected. By following these guidelines, it is possible to create safe and reliable electrical installations that meet the requirements of the NEC.